The research paper we decomposed is The Mechanics of Slithering Locomotion, and its purpose was to create a theoretical and observational model to study how snakes move on flat surfaces. It used 10 juvenile milk snakes that were placed in 9 orientations and tested on both a rough cloth and a very smooth fiber board that had low friction. They found that the snakes were unable to move on the smooth fiber board and that the friction was independent of orientation. However, on the rough surface, friction was anisotropic, meaning that the coefficient of static friction was greatly reduced in one direction but increased in the other. This was in accordance with the theoretical models that they created, where snakes were modeled as a one-dimensional curve of fixed length. So the conclusion was that the theoretical predictions were in accordance with the observations, and that due to the overlapping nature of belly scales on the snake, which caught onto asperities on the ground, locomotion of the snakes and the friction reduction is an isolation. We expect there to be functional similarities but structural differences between the milk snake scales as our bioinspiration and in Mamba Ramps as the design that we will be creating. Structurally, we cannot also create our snake scales from keratin, and instead we will be using steel and alloy. However, functionally they are similar because we will be using them in a similar environment, and we will be able to replicate the morphology of being textured and overlapping belly scales that reduce friction anisotropically in one direction, and also protecting the surface of the ramp from wear and tear. However, some functional constraints can be removed. While real snakes need to shed their scales and also have individual muscle attachments to their scales, our snake scale reproduction will be static, stationary, and does not need to be shed.
Our proposed trial design is a ramp for loading and unloading trucks. The ramp will be comprised of rotating panels that can be flipped with a lever. One side of the panels will be covered with a material that simulates the geometry of snake scales, taking advantage of frictional anisotropy to decrease friction on boxes and other cargo when being pushed up the ramp, while increasing friction stopping the boxes from sliding back down, given that the boxes are not extremely smooth. These changes in friction would make it easier to push boxes up the ramp and would prevent them from sliding back down the ramp if the person loading the truck should stop pushing. When the truck is to be unloaded, the panels can be flipped to the other side, which will be made of standard metal, allowing boxes to slide down the ramp normally without being affected by the increased friction of the snake scale material. This would make loading trucks with heavy cargo easier, while negating the need for peripheral equipment like dollies. The design you see here is a simplified version with only 4 panels, but a full-scale ramp would have many more, minimizing the space between panels.
If we were to carry out our design, we would need to collaborate with the company Roller Ramps to see how our design would integrate with theirs to increase efficiency. In addition, we would further collaborate with Robert Full, who is the bio-inspired design instructor at UC Berkeley. By collaborating with him, we would be able to discuss the limitations of our Mamba ramp. As for limitations discussed in our analogy table, we would need to further investigate if our product is feasible, since we would be using steel and alloy textured snake scales rather than keratin, which is found naturally in snake scales. Other than that, the only other major roadblock is that we do not fully know whether or not this bio-inspired design will work, since scales help snakes slither forward, but we are redesigning this inspiration to overlap scales to reduce friction in one direction. Since the product will be made in steel and alloy, we are not guaranteed for this product to work. In addition, we would test for the durability of this product, since snakes normally shed their skins 2 to 4 times a year. We would also need to test whether the product being made of steel and alloy would be the most feasible option, or if there are other material that would greatly reduce friction in one way but not the other.
Mamba Ramp is a bio-inspired ramp which makes it easier to push heavy objects upwards by using bars textured on one side with a snake scale inspired design. This bio-inspired design comes from the overlapping belly scales of the milk snake, which reduce friction in only one direction. On the Mamba Ramp, this makes it quicker and easier to push objects upward by reducing friction in one direction, but harder for them to slide back down by increasing friction in the other. When you need to unload, Simply turn a lever that isn't pictured here, which exposes the regular, untextured sides of the bars. Now you can enjoy easily both loading and unloading heavy objects.